like some only numbers were there, 9 minus 5 plus 2, something like that. Then we'll start studying about some strings, then how a complete program with the keywords of the programs, the syntax of the programs that can be converted into the parse tree. Because once the compiler is able to convert to the parse tree, then it becomes easier for the lexical analyzer, for the syntax analyzer, and for the semantic analyzer to take the role of compiling from the source code to the object code, or you can say the machine code. So we'll continue with this, and in this first thing what we will study is the tree traversal. This is a very important thing because probably you might have studied a little bit about this tree traversal in your data structure. You know what a tree is, right? So what the tree is, a tree having the first definition of tree is a tree can have a zero or non-zero number of nodes. If the tree is having a zero number of nodes, we say that is a empty tree, having no nodes in it. And if the tree is having non-zero number of nodes, then there are certain conditions, again, variations. Either the non-zero number can be 1, meaning the tree has only one node. So in that case, we say that tree is having only a root node. And if it is more than 1, then the tree is having a root node. Along with the root node, it has a left tree, it has a right tree, or it has a left child and the right child, and that way the tree is constructed. Usually the tree is a binary tree, that what we consider, and in this consideration, we assume that a tree can have zero number of child or one child, or it can have maximum 2 children. So that's what is a binary tree is. So when we talk about the tree traversals, it is the traversal meaning visiting the tree. That means you will make a tour around the tree, and the tour starts at the root node, usually scanning, and then it visits each of the nodes in the tree. That is what is the tree traversal. But how the visiting of the tree takes place, how the traversal of the tree takes place, that is most important, because as we studied about the expressions can be infix expression, it can be prefix expression, or it can be postfix expression. So depending on the kind of expression, usually the tree traversal is also done. So now we'll start with the tree traversal, then we'll study more about how this postfix traversals are being done, so that as we studied, any expression, if converted to a postfix notation, can be easily compiled or easily scanned or easily parsed by the compiler. So to start with, the tree traversals will be used for describing the attribute evaluation and for specifying the execution of code fragments in a translation scheme. So because we are studying about the translation scheme or the compilation scheme, what we understand. So this tree traversal is very important because it will teach us how to do the evaluation through the process of traversing the tree. So as I said, the traversal of a tree starts at the root node and visits each node of the tree in some order. There are different orders in which the tree will be traversed. So this is what is the one of the order that we'll study here. First is the depth first traversal, meaning the traversal goes too deep into one tree. You might have studied the depth first traversal or the breadth first traversal. Depth first traversal goes to the is as per the height of the tree, and it goes to the leftmost down node of the tree, whereas the breadth first, it works horizontally. It visits the nodes horizontally. So it is like visiting the left, right, and that way. So what happens in the depth first traversal? it starts at the root and recursively visit the children of each node in any order, not necessarily from the left to right. It doesn't have to go to left to right, but what it does, it goes deep into the tree one by one children itself. Meaning it is a recursive process. Recursive meaning, you know what is recursive, right? Recursive is calling itself. So if it starts from the root, it goes to the leftmost one, first left. Then from the leftmost, it goes to the next leftmost. It goes to the next leftmost. So that way it travels. So this is what is your tree traversal, or in the depth first traversal. It is called depth first because it visits an unvisited child of a node whenever it can. So it visits nodes as far away from the root, or it goes deep into the root as quickly as it can. So that is what is your depth first traversal of the tree. If you have studied about the depth first search algorithm, first search algorithm, that is also a kind of this tree traversal, and then that either it goes vertically or it goes horizontal. So you can see in the example figure, the depth first search, what it does, it first goes to the start node, the blackmost node at the top. Then it goes to the child of the first start node, that is the second black node. Then from here again it goes to the its child. So this becomes its next child. From here again it goes to the next child. So by this it goes to the last bottommost node of the path. So once it goes to the last black one, it finds that this is the leaf node, meaning it doesn't have any other child node. So when it doesn't have any other child node, it automatically goes to the next one. It goes to the parent from where it was inherited. So when it goes to the parent, it finds another child of the same parent. So it goes to that one. Now once that is over, it backtracks to the parent, and from the parent to the parent of its parent, and again the rightmost node. From this rightmost, again it goes to the in vertically down way, it goes there. Meaning what it does, every time it goes one by one deep into the Hello, anyone is asking any question?
No, ma'am.
Okay, thank you. So it goes deep into the one by one tree, and that is how the depth first search is, or depth first traversal of the node is done till the rightmost child or the last child is visited. This is what is your depth first search. Now, once we understood this depth first traversal, a syntax directed definition does not impose any specific order for the evaluation of attributes on a parse tree. There is nothing like that it has to go in that way or this way, but of course it is easy when it is being done in a depth first manner or depth first visiting way. Any evaluation order that computes an attribute A after all the other attributes that A depends on it is acceptable. So synthesized attributes, as we studied in the last class, what are the synthesized attributes? These synthesized attributes can be evaluated during any bottom of traversal. This is the reverse of the top down. It goes to the bottom of traversal. That is a traversal that evaluates the attributes at a node after having evaluated attributes at the children. As I said, it first goes to from the parent, it goes down till the children. Once the children visiting is done, it goes to the parent and it visits the other children of the parent. So that way it continues. Now, what is a translation scheme? We'll see what translation scheme is being used. So in this, the syntax directed definition builds up a translation by attaching strings as attributes to the nodes in the parse tree. So in this, what happens, the string will be added to the nodes or added to the, you can say, the grammar itself in the parse tree, so that they will be considered as the attributes of the nodes. And a syntax directed translation scheme is a notation for specifying a translation by attaching the program fragments to production in a grammar. This is okay. This is, I mean, nothing more to explain on this. So what it says, program fragments embedded within a production bodies are called the semantic access. Yeah, one more point I left here. A translation scheme is like a syntax directed definition. We have studied what is a syntax directed definition, except that the order of evaluation of the semantic rule is explicitly specified. So whatever program fragment we will consider that has been embedded within a production. Production means, you know, there is a head, there is a body. So whatever will be embedded in the production bodies, they will be called as the semantic actions. So the position at which an action is to be executed is shown by enclosing it within curly braces and writing it within the production body. Now if you see this statement here, now the action has to be taken at this point, print plus within quotation. So when the action has to be taken here, is this this has been enclosed in between the curly braces. You can see there are two curly braces, and writing it within the production body. So this is the body of the production, and where it has been written as plus storm print plus and the rest one. What the rest one says here is the, as I said, this is same as your rest. Thus the rest is a production of this, and the rest one and the rest difference, I think probably I told in the last class, this is nothing but the value at different time instant. So this is what has been mentioned. So when drawing a parse tree for a translation scheme, we indicate an action by constructing an extra child for it. Now because this was not there in our what do you say, body of the production, so this has been added extra, and this extra will be put in the curly bracket, and while doing the parse tree, this will be added as an extra child to the tree, connected by dashed lines to the node that corresponds to the head of the production. So the node which corresponds to the head of production, to that only this will be added as an extra child. We'll see an example of that. Here you see what is the to the node that corresponds to the head of the production. The head of the production is rest, right? So to the extra child is now added as print plus. This is added with the dotted line to this production, or you can say to the head of the production. So rest of the things remain same, plus storm and rest one, as in this plus storm and rest one remains same, but this extra where the action has to be taken, that will be added as a in a curly bracket as a dotted line to the head of the production. This is how it is being translated by the parser. So now you can see we had a tree. If you remember earlier, we had a tree for this 9 minus 5 plus 2. What was there in the tree? There was an expression. There was another expression. There was an expression which was 9. Then there was another expression. Here there was minus, and in this there was an expression 5. Then plus, then 2. This was the thing we had earlier. Now, when it is when actions are being translated, what are the actions to be taken? So here it does expression term, then it is this 9, and what is the action to be taken is print 9. So this is taken as an extra action here. So that is how it is written, print 9 with a dotted line. Similarly, here no action has to be taken, and in this terminal as 5 has to be taken as into the action. So we had this one, print 5, and here because this minus has to be taken. So here we have minus, and here you have again the print 2, and this plus is there. So every expression has now got one action that has to be taken, and that action is mentioned in terms of a dotted line and added to the parent of the tree, or you can say the notation into the tree. So you can see that in the above parse tree, the print statements are extra leaves which are attached by the dashed lines to the interior nodes that we have seen. The translation scheme appears in next slide. We will see how that has been translated in the next slide. But as of now, the underlying grammar generates expressions consisting of digits separated by plus and the minus signs. So we'll see that the grammar here is all this, the minus and the plus signs, the expressions are expressed in this way. So that's what it says. And the actions embedded in the production bodies translate such expressions into postfix notation. So whatever has been converted is now to the postfix notation, provided we perform a left to right depth first traversal of the tree and execute each print statement when we visit its leaf. So the translation scheme we'll see now. The translation scheme will be actions for the translating to the postfixes. This was earlier we had, if you remember, expression is a production of expression plus term. So here the action taken has to be plus, and expression 1 minus term. Here print has to be minus, and expression will be at the form of term, where term is equal to 0 to 9. So every time the print will be 0 or 1 or 9, that is the action to be taken. So these are the actions for the translating it into the postfix notation. That is what is the actions for translating to the postfix. Now here the root of the tree represents the first production. As if you can see, this is the first production expression. In a post-order traversal, we first perform all the actions in the leftmost subtree of the root. Because we have seen postfix means first the left, then the right, then the middle comes, or the root comes. Right? 9 minus 5 meaning first 9 goes, then 5 comes, then the root or the middle one comes to the right. So that's what it says. In a post-order traversal, we first perform all the actions in the leftmost subtree of the root, then for the left operand, and also labeled expression like the root. Then we visit the leaf plus at which there is no action. You can see here. It goes there, and when there is no child or nothing leaf node occurs, then it has to revisit or it has to come back. We next perform the actions in the subtree for the rightmost operand term, and finally the semantic action print plus at an extra node. That is being done. You will see here. Here is the thing that is being done. So first 9 is printed, then 5 is printed, then your minus is being printed, then it goes to 2 is printed, and finally it goes to the plus. So your expression will be 9, 5, minus 2 plus. This is what is the postfix action. So for this 9, what is the action? 9 will be printed. For this 5, what is the action? 5 will be printed. Then for negative this minus, what is the action? Here print minus will be printed. Then your 2 will be printed, and finally your plus will be printed. So this will be the action of the result of this 9 minus 5 plus 2 in the parse tree. And this was expected. This was the outcome of the parse tree for this.
And this function is
Hello. Yeah,
When something is painful,
your audio is not clear. Are you asking any question? Okay. So since the productions for Tom have only a digit on the right side, that digit is printed by the actions for the production. That's what I said. The action that has to be done is the print. So that way it does the production. It is translates the production and does the action accordingly. No output is necessary for the production expression is Tom, and only the operator needs to be printed in the action for each of the first two productions. So when executed during a post-order traversal of the parse tree, the actions print 9, 5, minus 2 plus. As I said, the action to be taken is just the writing of the numbers or writing of the digits. So accordingly, the print action will decide what has to be written and how it is written, so that in the extra node of the root, it does the action of writing the digits. Now we have studied something, the schemes in slide 58 and 71 produce the same translation. They're constructed differently. We'll see now. Just let me. So it says the slide number 58 and 71 produce the same translation, but they construct it in differently. We'll see how they do. 58 and 71. If you see this, sorry. The outcome of this one is, as we studied, 9, 5, minus 2 plus, right? This is the outcome of this tree or this action to be taken. Now the other one what we studied in slide number 58 is almost the same. See, this is what we studied here. This is the syntax directed definition for infix to the postfix notation. So here also what we got, the outcome was 9, 5, minus 2 plus. This was the outcome of this one. So what it says, the same code can be translated in any of these two methods, so that we get the same output what we got in this current expression. But slide 58 attaches the strings as the attributes to the nodes. As we said, .t, tom.t, and expression.t. So that says the attributes are being added there to the nodes in the parse tree, whereas slide 71 prints the translation incrementally through semantic actions. Here we don't attach the attributes to this, but we simply express or we simply translate it, so that by writing an extra action of write or print statement, we get the outcome in the similar way. The implementation of a translation scheme must ensure that semantic actions are performed in the order they would appear during a post-order traversal of a parse tree. So what it says, the implementation did not actually construct a parse tree as long as it ensures that semantic actions are performed as if we constructed a parse tree and then executed the actions during a post-order traversal. So we understood what a post-order traversal does. We understood how the semantic actions are being taken, what are the actions are being taken, how these actions are added to the parse tree with a special dotted lines, and what is the result of this semantic analysis or semantic result in the construction of the parse tree. So with this, we come to the actual target. What we wanted to do is the parsing. Meaning, when an instruction is given to the compiler, It does the job of parsing. So how it does the parsing? Once parsing is being done, meaning your coding has been scanned, character by character, word by word. Your terminals, your non-terminals are identified. Your identifiers are identified. Your keywords are identified. Your operations are identified. So everything has been identified individually with importance. Then it will fed to the what do you say, the lexical analyzer, and lexical analyzer will start analyzing it. So parsing is the process of determining how a string of terminals can be generated by a grammar. As I said, let's say I say my name is X. Instead of the grammar, we have a grammar for that. Mine, then the subject name, then we add the verb is, then we say the name. So this grammar will generate actually how a English has to be written. It teaches us how to write an English statement. So here also it is a parsing, means it teaches or it says how a string of terminals can be generated by a grammar. So it is helpful to think of a parse tree being constructed, even though a compiler may not construct one in practice. When we give the code to a compiler, when you write in the C statement, scanf A and B, C is equal to A plus B, printf C. When you write these three statements, do you think that the compiler or the C compiler creates a parse tree, what we are seeing here? It is not, because it doesn't create, there is no space that it will create a parse tree and it will do that. What it does is, it generates a code as per the parse tree, and that is being stored in the memory. So when the memory will be scanned, automatically this will be treated in the same way as we are studying the parse tree. That is the reason why we make a parse tree, because we are understanding the whole thing in the concepts of a tree. Because that is, we can see a tree, we can visualize a tree, we can understand a tree. So for our understanding, we assume or we think or we analyze this, that the code is converted to a parser or parse tree. So it is for our practice, for our understanding, we do it. But in actual, the code doesn't make a tree shape, or what do you say? Pictorially, it doesn't make a tree. But yes, whatever it converts or whatever it translates is similar to the concept of a tree. That is why we say parser does the or creates the parse tree. However, a parser must be capable of constructing the tree in principle, or else the translation cannot be guaranteed correct. That's what it says. If a parse tree is not being designed properly, a parser is required to design or to translate the code into a tree structure. So I think this we have already studied, the types of the parser. And now coming to this, we go to the top-down parser. This probably I have told you. Here is the top-down parsing. Now we'll see a small example of a top-down parsing. What is top-down parsing here? You'll see that there are two things. One is there is a code written, and another is a tree of the code has been generated. So what is there in the code? The code says that there is a statement, and this statement is nothing but a production where the body is a simple expression, or the body can be an expression within parentheses with a keyword if expression then statement, or it can be the expression with three variables, first, second and third. We know how you write a tree for statement. So when you write a for statement, you write in this way. So what it says, for then three expressions and then a statement, or it can be any other statement. This is how we write a statement in C. Let's say C or Java, any programming language you can say. Let us assume for simplicity, we write this in C. And what is this opt expression? This opt expression can be a null or it can be an expression. Meaning if I say for I is equal to 0, I is equal to 5, I plus plus. Meaning for I is equal to 0 to 5, the statement will be executed. Or if I don't want to say anything, I may not put any expression here, or I may put an expression here. So this is what is a statement, how we write a C program in our own language, that is in the high level language or the user language. When this will be converted to a parse tree, the parse tree will be like this. So what it says, it starts with the root statement, the head of the production. So now this starts with the statement. Then one of the child of the statement is, if I say this one, the for one, the longest one I can say. The first one is for, then the left parenthesis, then opt expression, then colon, then another opt expression, then colon, then opt expression, then the end of your parenthesis, and then you have the statement. This is what is the tree, or this is what is the parse tree that has been written. Now with this we can further expand the parse tree like this. What is that? Your opt expression can be a null, meaning you don't want to put any column there or any expression there. If there is no expression mentioned, meaning it is a null statement. Or you can have expression for all three opt expressions, right? Any of this can be a null, any of this can be an expression, and the statement can be in any other statement, right? So this is what is one of the parse tree of your statement like this. And if the compilers goes for this in a post order traversal, what it does, it first checks for, then it goes to left parenthesis, then it goes to statement, where it again goes to the opt expression, then it goes to the semicolon, and that way it scans the whole of the tree and the translation is done accordingly. So this is what is the one of the small example of your top-down parsing. So we'll see how the things are being done. So here what it is used is single terminal symbols, that is if and for. We know what is a terminal. Terminal is nothing but the keywords. So what are the keywords here? The keywords are if and for. So these are the keywords if and for here. And terminal expression represents the expressions. So here expression meaning it represents the expressions. And other is a terminal representing other statement constructs. That means other here we are using can be any statement which has not defined yet. So the top-down construction of a parse tree is done by starting with the root labeled with the starting non-terminal statement. The root comes with the non-terminal statement because the statement can be anything. So it starts with a non-terminal statement as the root and repeatedly performing the tasks. So what are the tasks it does? The first task is at node n labeled with a non-terminal a. Let us say in this, at any node with a non-terminal a, let's say opt expression is a non-terminal which can be assigned as a. Select one of the productions for a and construct the children at n for the symbols in the production body. That's what it has done what it has done is, for any statement, for any terminal A, what it has done, it has done the product for the production, it has done the tree, like all this statement has been written. And for any interior node, let's say for this one, it also constructed the tree with the epsilon as one of the child of it. And second one is, find the next node at which a subtree is to be constructed. Typically the leftmost unexpanded non-terminal of the tree. So this is how the tree is generated from the your code that you have written. Now for some grammars, the above steps can be implemented during a single left to right scan of the input string. As I said, if you scan this expression for left parenthesis, all this, it can easily scan all of these components or all of these elements of this statement, and those can be written. So the above step can be implemented during a single left to right scan of the input string. The current terminal being scanned in the input is frequently referred to as the look ahead symbol. So these symbols or these terminals, the whatever has been used here, the input here are called the look ahead symbols. So what are the terminals here that has been scanned and the input, and we continuously refer to them as the look ahead symbols, and these look ahead symbols will be further used for the making of the parse tree. So what it says, initially the look ahead symbol is the first, that is the leftmost terminal of the input string. Let us go to the example. The first one is the look ahead is statement. So this is the first statement, or it comes to the, it is the first or the leftmost terminal of the input string. So if we consider one input string, whatever will be the leftmost terminal, that will be considered the look ahead symbol. Now the construction of the previous parse tree for the input string for this expression other is shown below. So for this one, how we can make a construction of the parse tree, we'll see now. What it says, initially the terminal for is the look ahead symbol. This is what it says, is the first leftmost terminal of the input string. So the for is the first leftmost terminal. Now this will be treated as the look ahead symbol. And the known part of the parse tree consists of the root labeled with the starting of the non-terminal statement. We'll see now the root, whichever will be beginning, that will begin with the starting of the non-terminal statement. So here you will see parse tree for this for expression, and this your parse tree is like this statement, because it comes to the for. If you go to this statement, what it says, statement for this the thing. So first one is your look ahead symbol, and its head of the expression or head of the production is the statement. So your table starts, or the parse tree starts with the statement here. This is the root of the statement or root of the parse tree. The objective is to construct the remainder of the parse trees in such a way that the string generated by the parse tree matches the input string. So whatever will be generated in the parse tree, that should be same as the input or the statement used in the program. That is what is the objective. So how it can be done, we'll see. If you'll see here, yeah, we'll study so that with example to this we can go. So for a match to occur, the non-terminal statement in A must derive a string that starts with the look ahead symbol for. If you'll see this one, how a matching occurs. The first non-terminal is the statement. It has to derive a string that starts with the look ahead symbol for. So here you have the statement and the string matches with the first one, that is the for. It starts with the for, as in the figure A. And in the grammar of this earlier one, there is just
चटनी भर लिया वो पीता है
there is just one production for the statement that can derive such a string. So we select it and construct the children of the root labeled with the symbols in the production body. So how this is expanded, we'll see. It has been expanded like your head of the production goes here, and subsequently the look ahead symbol comes here, and then the input for this goes with the scanning of each of these characters in the parse tree. So for this, it goes as the first semicolon because opt expression is null. So we can make it null, and the opt expression is termed as the expression here. This opt expression is expressed as the expression here, and the statement can be other, as it has been in one of the production. Statement is like can be also have the form of other. So I am putting in the other here. Now for this table, now we'll see that how the input does match or not. Now for this, this becomes your look ahead symbol, and this look ahead symbol matches with the earlier one. So that means every time it goes to a look ahead symbol, it checks whether it matches to the input string or not. If it matches to the input string, we can say that the parsing tree that, or the parse tree that has been generated is of right match or of the correct one. That's what it says. The expansion of the parse tree is shown in B. Slowly the parse tree has been expanded. Now each of the three snapshots in the figure has arrows marking the look ahead symbols. As I said, the arrows are showing the look ahead symbols. Initially it was for. Here then the second case also this is the for. In the third case it goes to the left parenthesis, and so on and so forth. It continues till all the symbols will be scanned, and they will be considered as the look ahead symbols and proceeded further. So each of the three snapshots in figure has arrows marking the look ahead symbols in the input and the node in the parse tree that is being considered. So once the children are constructed at a node, we next consider the leftmost child. Once all the children are constructed, we start scanning from one by one the leftmost child. As in figure B, you can see children have just been constructed at the root, and the leftmost child labeled with for is being considered. So when the node being considered in the parse tree is for a terminal, and the terminal matches with the look ahead symbol, then we advance in both the parse tree and the input. So here what it says, the look ahead leftmost child of the look ahead symbol, that is for, matches with the terminal. Our terminal is also a for, right? So when this matches, we can proceed further for the next of the steps of the parse tree. This is how a further advance will take the arrow in the parse tree to the child labeled with the non-terminal opt expression and take the arrow in the input to the terminal semicolon. This is how you're proceeding each of your terminals or each of your symbols in the parse tree that goes there, and finally it is treated as the correct parse tree for the symbol. Now at the non-terminal node labeled as opt expression, we repeat the process of selecting a production for a non-terminal. And as I said, a production with epsilon or a null value as the body requires special treatment, meaning we don't have any element in the expression. So how that can be done? So for the moment, we use them as a default when no other production can be used. With non-terminal opt expression, this is an opt expression is a non-terminal because that is user defined, and the look ahead semicolon, the empty production is used since semicolon does not match the any other production for opt expression, which is terminal expression as its body. As you will see, we have given a null value. Null value meaning there is no opt expression here. So because there is no opt expression, we can give a null child, or you can leave an empty child for this. That is what is a null expression. For the moment, we use them as a default when no other production can be used. So with non-terminal opt expression and look ahead, the null production is used. Since semicolon does not match the only other production for opt expression, which has terminal expression as its the body. So this is how your code of C or Java is transformed to a parse tree. In general, the selection of a production for a non-terminal may involve trial and error. That is, we may have to try a production and backtrack it to try another production if the first is found to be unsuitable. As we discussed, if there is an unmatch between the production and your parse tree, it has to backtrack to check whether there is any error or not. Otherwise, the same will proceed further. A production is unsuitable if after using the production, we cannot complete the tree to match the input stream. That's what I said. We cannot say a parse tree or a production is suitable or correct if the parse tree that you design doesn't match with your input stream. If it matches, then it is the right parse tree. If it doesn't match, it's not the right parse tree. So here some of our example of the top-down parsing is there, where we can see that suppose the given production rules are as given like this. In this case, we can see that the production rules are like the symbols or the your start symbol is S, and having the production as A or D, or it can have in the form of A and B. So in any of the cases, you will see that it has the value of this, or A can have B or C. So A has the value here, A can have B, or A can have the C value. So here also S has the value of A and B, where B can be C, C and D. So this is how the top-down parsing is being done. It's a very simple case of doing the top-down parsing. So with this, if we find there is no match in case of your input tree or the parse tree and the input string, then we assume that there exists some errors, and this error can be treated as an important issue, or you can say it has to be eliminated by some of the rectifications, and those things are being presented in the lexical errors. Now coming back to this, I'll just come back to the lexical errors later, but for the timing, let me go through the few of the other things. Yeah, so once we have the parse tree with us. Now this parse tree goes, the output of the parse tree goes to the lexical analyzer. Now it is the job of the lexical analyzer who has to go through, or who has to see the total analysis of the parse tree, or scan each bit by bit, and it will fix any of the bug that is available in the lexical analyzer. So sometimes what happens, The lexical analyzer needs to look ahead some symbols to decide about the token that is to be returned. So in C language, we need to look after the symbols like minus, equal to, or less than to decide what token to be returned. It's like in Fortran, what we do some label number, the 5 is a label number, right? Then the identifier I is equal to 1.25, meaning it is a kind of statement that has to be executed. So we need to introduce a two buffer scheme to handle such a large look ahead safely. Now how this can be done, we'll see. As we have seen in one of this okay, E is equal to MC square, as we saw. There is a if in this form, if you write E is equal to M star C star double star or exponential square, that is 2, and then occurs your end of file. If this occurs, how the buffer or how the input buffer takes place and how it can be generated, that we'll see. So before that, before I go for the sentinels and all, just we'll take a break and then we'll come back. We can take a break for 15 minutes, then we can come back. This I can directly share with the material, which will be easier for you to understand, because I said this is the I mean very useful book, and you can refer this book. Most of the contents that I am teaching is from this book only, with some little variation from the other book. So if we can understand this from the Aho and Ullman book, that will be easier for you to understand as well. And you can also refer this book for the details of this, I mean your syllabus studies, because this is a very, I mean very popular and mostly used by the undergrad students. So if I save some from this, maybe for the rest of the class for today, I'll just quickly cover this predictive parsing and some of the portions from this. Then tomorrow again we'll back to our normal material and we can do that. So instead of copying this content from this book and all, so I thought I'll just share it here, so that you can see and we can go through this predictive parsing and now. Are you able to see this material, right? Okay. So what it says, the predictive parsing, it says that the recursive descent parsing is a top-down method of syntax analysis, and in which a set of recursive procedure is used to process the input. As I said, recursive procedure means the procedure will be called repeatedly, called one by one, and one is this procedure associated with each non-terminal of a grammar. So when we decide one is the terminal of the grammar, another is the non-terminal of the grammar, the procedure will be always associated with a non-terminal of a grammar. And we consider a simple form of this recursive parsing, which is called a predictive parsing. So what is predictive parsing? We'll study in details of that. In this predictive parsing, what happens? The look ahead symbol determines the flow of the control. So by now what we studied, the look ahead symbol is the first or the leftmost symbol of your expression of your production. That is the look ahead symbol, and this look ahead symbol determines the flow of the control. Whether the flow will go, as I said, the scanning of each of the characters in the expression, that will be decided from the look ahead symbol through the procedure body for each of the non-terminal. So the sequence of procedure calls during the analysis of an input string implicitly defines a parse tree for the input and can be used to build an explicit parse tree if required. We'll see that there is a predictive parse tree in this figure. I'll just go through this. See, there is a, recursion, right? You have written the programs in recursion. So if you have written in recursion, you can understand this. So this is a predictive parsing. We'll start with this. So your production or the start symbol starts with the statement, like the root of your parse tree, that is the statement. And it goes with the look ahead symbol. As I said, when it starts, it first comes the look ahead symbol, the first symbol. So in this first symbol, what it says, it checks for the expression. If expression, the case of expression, then it matches with the expression and then match with the semicolon and break. So this is a case statement saying for different values of the look ahead, or the different values of the case statement for the expression. It checks whether the match statement is there or not, if the matching of the expression exists or not, and then otherwise it goes for the next case statement, which is a if statement. So this if statement checks whether there is a match with the if or not, if there is a match with the left parenthesis or not, if there is a match with the expression or not, and if there is a match with the right semicolon or close parenthesis is that. So this is another statement for if statement. And there is also a similarly case for the for statement, for a for and all this thing, everything. And there is another case for the other statement. So now it will say the match with the other, if that exists or not, and break. So by default, it will say that if it doesn't exist any of this, it will report that syntax error. So any of this, if exists, that will be treated, or that will be considered as the parse tree, that will be processed as the parse tree. If not, then automatically it will be written as the syntax error. So when it goes to the module, it checks for the opt expression. What it checks, if the look ahead is equal to expression, if that is true, and for the terminal, for the match terminal, it checks for the, if the look ahead is for the T, or the look ahead is for the next terminal. So that way, if not, then it says that there is a syntax error. So your whole of the coding, or whole of the parse tree or the predictive parsing is dependent on on this pseudocode, and which says whether there exists a syntax error or not. You most of the time when you write a code, you see that there is a syntax code, right? So if when the syntax code occurs, a syntax error, when that syntax error occurs, meaning your predictive parsing or your symbol table that has been considered is not matching with what it should have been. That is why you get the error of syntax error, right? So in this, what it says, the predictive parser of the code pseudocode that we saw, it consists of the procedures for the non-terminals. One is the statement as the non-terminal, and the other one is the opt expression. These are the two non-terminals of the grammar, and you understand or you remember why they are the non-terminals, meaning they are user defined. They are not the keywords, right? So, and we have already seen that an additional procedure match used to simplify the code for the statement and opt expression. So the procedure match T compares its argument T with the look ahead symbol. If you'll see here, the match is compared with the, yeah, so this match is compared with the T, the expression, the terminal T. So to find out whether there is the look ahead table matches with the T or not. If not, then it reports that there is a syntax error. And this occurs recursively. So because it occurs recursively, it checks for each and every character in your code. Maybe you write in any language, maybe you write in C or Java or any language, Fortran, wherever in whatever language you use, in every language, the look ahead symbol will be compared with your code or with your procedure so that it can find out that whether there exists a syntax error or not. So this is what is the first step of your compilation or first step of your, you can say, translation from your source language to the object code. That is why your first statement or first step of your any program executing your program is compiling. If you know that first it has been compiled, then it is being executed. So during this compilation stage, your code is converted to the parse tree, and then the parse tree is checked character by character to see whether the constructed parse tree matches with your input string or not. If it matches, your parse tree is correct. If it does not match, there is an error. So there is an error in the construction of the parse tree, and that error occurred because your recursively generated parse tree does not match with the input symbol. And that is why there is an error, and this error has occurred. So you get a message of syntax error. Most of the time you might have got the syntax error. So once you rectify it, you get that it is rectified or it has been fixed. So here it says the procedure match T compares its argument T with the look ahead symbol and advances to the next input terminal if they match. So every input terminal will be matched for the string. Thus, match changes the value of variable look ahead, a global variable that holds the currently scanned input terminal. If you see in the code, this code is most important. So I am trying to explain this from this material. So you see, every character is matched with your look ahead T. So it says that the first look ahead will compare with the existing T, and then it will go for the next look ahead. So what is the look ahead is the next terminal. So once first T is the terminal, right? So it is matching each and every terminal of your code. So first what it does, it checks for the first terminal, that is the first T, and if it is yes, I mean if it is correct, it goes to the next look ahead. And what is the next look ahead? That is your next terminal. So every terminal of your code is being scanned one by one, and then it says that there is no error in your code. If at any point this matching is not coming as true, your match of the terminal is not true, it will report that there is a syntax error, right? And how this is being called? This is called with this look ahead expression match. So what it does, and this is the opt. This is the opt expression, and this opt expression says that if look ahead is equal to the expression, then go for this match operator. So if there is there exists any symbol or any expression, it has to be matched. And to call the match or that call the procedure match, this one is what this opt expression is executed. So this opt expression calls the match. The match does the matching of every terminal by saying whether the expression syntax error is there or not. And this opt expression is now called here, you can say in the main program. So here you will see if it is an opt expression, for normal expression, there is also a match expression, and there is a match semicolon also, because semicolon is not considered as a terminal. So this takes a separate expression as a call by value, you can say this match and this match will be invoked with a call by value expression. And for if also, it does match if. So this if will be called by the value that will be treated as the terminal, and then match with the left parenthesis. Here it will call this as a terminal will be as the left parenthesis. Then match will be with the expression. Then match will be with the your right parenthesis, and then the statement will be there. So here also for statements also the match will be there for each and every character. And whenever there is an opt expression, it automatically goes for the look ahead. And if the look ahead is there, then again it goes for the match expression. So the point of saying this code or this pseudocode is most important in case of your predictive parsing. The reason behind is it explains here. This is the actual pseudocode for your predictive parser. You can see these two small modules are very important, and they say how a look ahead table compares each character of your code treated as a terminal node, a terminal or non-terminal, and says whether there is an error or not. So because I could not make the slide for this, so I'm just sharing this one. If you have the book on this book, your Ahon Ullman book, you can just go through this one. This is a very important, predictive parsing thing. If you can understand this, your whole of the parsing concept will be very, very clear. So this is what it happens. We can just go through the theory of this. Yeah, here it explains. Just let us see let's see how it explains this. So the parsing begins with a call of the parsing begins with a call of the procedure for the starting non-terminal statement. We'll just see here the non-terminal statement. This is what it calls. With the same input as this. So look ahead is initially the first terminal for. The first terminal is for. So your look ahead goes for the first terminal is for the for statement. That has been assigned earlier because look ahead was the first is the for statement for match. So statement is for opt expression this one. This is the first look ahead symbol as we have seen. So procedure statement executes the code corresponding to the production. Statement can have the form of for and these three. So this is the first expression that has to be put inside the predictive parser. So what happens now? In the code for the production body, that is the for. Here is the production body, right? The right side is the body. So the for case of the procedure statement. So this is the statement. Each terminal is matched with a look ahead symbol. So each of these terminal, the for, the left, the opt expression, the semicolon, everything is being matched with a look ahead symbol. And each non-terminal leads to a call to its procedure. What is the non-terminal? Opt expression. Opt expression is a non-terminal, so it leads to a call of its procedure. What is the call of procedure? Opt expression is a call. So two calls are there. One is match, another is the opt expression. So match is for the for your look ahead symbol matching, and opt expression goes to the this call, which ultimately calls your match expression again for the look ahead symbol. So this is what it does in a recursive way. Yes. And each non-terminal leads to the, this is what is very important. The terminal is matched with a look ahead symbol, and the non-terminal leads to a procedure call of this procedure. So this is what is the basic gist or theme of the whole of the pseudocode, where it can follow the rest of the things in an iterative manner or recursive manner. So in the following sequence of calls where we say that match for, match left parenthesis, opt expression, this is a again another separate non-terminal expression call. Sorry. Then match semicolon, opt expression, then match semicolon, opt expression, match right parenthesis, and statement. So whenever there is a non-terminal for the statement and for the opt expression, it calls the module. And whenever there is a terminal, it calls for the symbol table matching with the code match. So this is what it says, how the symbol table is being, or the look ahead symbol is being matched, and the non-terminals are called repeatedly. So here it says the predictive parsing relies on information about the first symbols that can be generated by a production body. And more precisely, let alpha be a string of grammar symbols, maybe terminals or maybe non-terminals. We define first alpha to be the set of terminals that appear as the first symbol of one or more strings of terminals generated from alpha. And if alpha is a non or empty symbol, you can say, or can generate an empty symbol, then this epsilon is also in the first alpha. So this is of not that importance. We can skip this one. So now I think you understand how this is being done. The pseudocode is done for this. So it says the first statement means first alpha, you can say. The if statement is the alpha, then it goes for the expression, if for other. And if it is an expression, it simply goes to an expression, because some expression semicolon, it goes to the expression. So the first sets must be considered if there are two productions. One production is A can have the form of alpha and A can have the form of beta. These are the two productions, you can say. So ignoring the epsilon productions for the moment, predictive parsing requires first alpha and first beta to be disjoint. They should not have any link between them. So they need to be disjoint. And the look ahead symbol can then be used to decide which production to use. If the look ahead symbol is in the first alpha, then alpha is used. Otherwise, if the look ahead symbol is in the first beta, then beta is used. So what it says, when you have this alpha, you take as the statement, and beta you take as the expression. So what it does, it checks for whether it has to be the symbol has to be alpha has to be taken or the beta has to be taken. Meaning the expression has to be taken or the expression if for other this has to be taken. So accordingly it decides.
Excuse me, ma'am, sorry to interrupt. I just want to know that this first statement expression if for other, that part is not clear to me. Just will you please explain it once again?
Okay. So let's go to this one. If you want this, I can explain this. Here it is written the C. So let me repeat this one. It will be easier for you. The predictive parsing relies on information about the first symbols that can be generated by a production body. You remember what is a production body, right? Production head and production body. So if a production body generates a symbol, that we'll consider as the, So more precisely, let alpha be a string of grammar symbols. Grammar symbols means your grammar symbol can be a terminal or it can be non-terminal. So we are assuming a string of symbols or string of terminals and non-terminals to be alpha. That is the first thing. And we define first alpha. This is the procedure, first alpha, to be the set of terminals that appear as the first symbols of one or more strings of terminals generated from alpha. So if alpha is a string of grammars of terminals and the non-terminals, then and we are using a function first alpha, this is to be the set of the terminals that appear as the first symbol. First symbol, what is the first symbol? Meaning the first character that you are going to match as the look ahead symbol, right? So what happens? So if this appear as the first symbol of one or more strings of terminals generated from alpha, then alpha is epsilon or can generate epsilon, where epsilon is also in the first alpha. Meaning your first alpha is can have a null value, or it may not have a null value. So depends on whether there is a look ahead symbol matching occurs or not. So to have this, the details of how one compute the first alpha will be seen in the subsequent classes. But here what we understand is we shall just use the ad hoc reasoning to deduce the symbol in the first alpha. Typically, alpha will either begin with a terminal, which is therefore the only symbol in the first alpha, or alpha will begin with a non-terminal whose products and bodies. Now, non-terminal means it is a user-defined identifiers, right? So if it begins with that, then the whose products and bodies begin with a terminals, in which case these terminals are the only members of first alpha. So with this example, what it says, with respect to the grammar in figure 16, the following are the correct calculations of first. We'll see what is the figure 26. Just a minute, if we go to this. You have something, this one, this figure 16, you see, you have, if you remember this statement can be an expression. Statement can have the form of if expression then statement. Statement can have the expression for opt expression 1, 2, 3 then statement. Then statement can have the option of other, where this opt expression can have a null value or it can have an expression. This is what is the grammar we studied. Now let us put this in our alpha and beta case. We'll see how it appears. So for example, with respect to the grammar that we studied, the following are the correct calculations of first. See, the first sets must be considered if there are two productions. A can have the form of alpha and A can have the form of the beta. This one. First is the statement, where statement equal to expression if for other. This is alpha is the set of terminals, right? If you remember. So this is all the terminals expression if, for and other. And first is the beta, and where beta is the non-terminal, or first can have the expression, then semicolon, it can have the value of expression. So the first sets must be considered if there are two productions alpha and beta. Ignoring the null value productions for this moment, predictive parsing requires first and the alpha and the first beta to be disjoint. The look ahead symbol can then be used. The look ahead symbol here is your for symbol. That was the look ahead symbol. Can be then used to decide which production to use, whether the production A tends to alpha will be used, or A can have the value of beta has to be used, where alpha is the set of terminals and set of A is the beta is the set of non-terminals. So which expression will be used, whether the terminal expression has to be used or the expression non-terminal expression has to be used, that will be decided by this. So if the look ahead symbol is in first alpha, then alpha will be used. Alpha means the set of terminals will be used. Otherwise, if the look ahead symbol is in the first beta, then the beta will be used. Beta means the non-terminals will be used. So whether there will be in terminals like if, for, semicolon, all those things will be used, or the non-terminals like opt expression, statement, those will be used. So it depends on which of this alpha, first alpha or first beta will be considered, or that will be lead to the result of whether the parsing will go for using the terminals, or parsing will go for the using the non-terminals. We'll see. Subsequently, we'll see more on this predictive parsing. The things will be more clear if we'll go for the examples later. So this null productions, it's of not that much important. We can that, yeah. This way we can see. So how this predictive parser can be designed. So why we look for this predictive parsing, and how this can be designed. To say this, we can generalize the technique introduced informally in this to apply to any of the grammar that has disjoint first sets for the production bodies belonging to any of the non-terminals. That means it goes to the beta one. So we shall also see that when we have a translation scheme, that is a grammar with embedded actions, it is possible to execute those actions as part of the procedures designed for the parser. So recall that a predictive parser is a program consisting of a procedure for every non-terminal. As we studied, there are two things. One for the matching of the terminals, another is for the non-terminals. So matching of the terminals says whether there is a syntax error or not, and the calling of the non-terminals also decides whether there can be a non-terminal or not. There can be an error or not. So the procedure for non-terminal A has two things that usually do two things. What it does, we'll see. It decides which A production to use by examining the look-ahead symbol. The production with body alpha, where alpha is not null or the empty string, you can say. Where alpha is used if the look-ahead symbol is in first alpha. If there is a conflict between two non-empty bodies for any look-ahead symbol, then we cannot use this parsing method on this grammar. In addition, this probably I think I can explain with an example, will be more clear instead of saying this. Let me go to the slides, just a minute. Okay, I can explain this. Yeah, what I'll suggest is I'll prepare its slides properly. Probably I have some random slides on this, but that doesn't work. Okay, I'll do one thing. This for this predictive parsing and all. I'll just prepare the materials and prepare the examples properly. That would be easier to understand. You can comfortably do that. No, let it be. So what we can do is Professor Chakravarti, are you there?
Yes, ma'am. I am.
Yeah. So what I'll do, Professor Chakravarti, actually, I was thinking to explain the things from the material, which actually I could not prepare, unfortunately. I was thinking to explain that the predictive parsing and all. So can we, I mean, extend this tomorrow? Tomorrow I can say, I mean, prepare all that so that I can explain. Because I'm having some random slides and doesn't make any sense if I do that with the random slides. So instead, I'll prepare it with an example so that I can stay tomorrow.
Okay, ma'am.
These slides will be given to the students as well, right?
Yes, ma'am. You can share with me, and then I will send it to the student.
Okay. So
Okay,
I'll prepare the slides and then rest of the things I can tell tomorrow because today
okay, ma'am.
I could
There
not
is no
prepare
issue.
it. Okay. So
Okay,
because
ma'am.
of
There
the
is no
meeting,
issue.
as I said, I was in the meeting in the whole day and the class in the morning, so I could not prepare it properly. So I can stop it today and now I can continue tomorrow.
Okay, ma'am. There is no issue.
Okay.
Thank you for this wonderful session,
Okay.
and thank you to everyone to attend this session. We will again meet tomorrow at 2:30 p.m.
Yeah.
Okay, ma'am. So thank you.
Tomorrow is a holiday for me, so should not be any issue. And we can continue on time. We can start on time by 2:30.
Okay, ma'am.
And
There is no
okay.
issue.
Yeah. Okay then. Thank you. Thank you all.
Okay, ma'am. Thank you.
Thank you, ma'am. Thank you, sir. Thank you, ma'am.